Hello, everybody. So I hope everybody's interested for yet another WebAssembly Component Model talk. Okay. Yeah? That's the enthusiasm. I'm a bit surprised. Nice. So today, what we wanted to do is we want to show you our journey where we wanted to apply the component model to the Kubernetes scheduler. So my name is Dejan Pejchev. I'm an open source engineer with the G Research open source team. So together with my colleague, we'll try to walk you through our journey, through the road bumps we encountered. So Jonathan, if you may.
Yeah, so hi everyone, I'm Jonathan. I also work for G Research in the open source team, and I work on all kinds of things that are open source in pretty much any programming language, and always with a focus on performance and maintainability. And so first, I want to do a little previously. In episode 1 of Dejan and Jonathan Go to KubeCon. So back then, we discussed the magic behind the Kubernetes scheduler and the various ways that you can extend it. If you are interested in this and you missed it the last time when we were in Salt Lake City, I would highly recommend you go ahead and watch our talk, but not right now, obviously, just half an hour, because we're not going to talk about it in more details now. I'm just going to try to give you enough context to appreciate the next 25 minutes, hopefully. So last time, we looked at the whole scheduling cycle and all the places where you can hook your own code into it. And as you can see on that picture, there's quite a few. And then we explored the 3 ways that you can hook your code into that. So one of them is the scheduler extenders, which is basically webhooks. You can write this in any language, and it's just JSON over HTTP. Obviously, you'll have a fairly high latency because it goes over the network, and there's only just 4 places you can extend. This is basically legacy stuff. The other one is the scheduling framework plugins. That is like the big boy stuff, where your code ends up being part of the scheduler itself, and you have to deploy a custom binary of the scheduler plus your code. That is super efficient because you're completely entirely native Go code, but that's not very flexible in terms of deployments. And also, there's more than a dozen extension points, basically all the ones you saw in the previous slide. So you can really go crazy in terms of implementing your own custom logic. And then finally, we showed the WASM plugins. Yeah, so we're going to say WASM a lot today. WASM means WebAssembly. So who's familiar with it in the audience? Okay, cool. That's quite a few people. Just for the other ones, very briefly, WebAssembly, it's portable across architectures, you know, ARM, Intel, etc. It is sandbox during execution, and you can target it from many programming languages. It's a bit like the old Java write once, run anywhere, except that there's way more languages that you can use, and it is sandboxed from the start. So, WASM plugins, let's dive slightly deeper. You've got your Kubernetes scheduler, and this time you deploy the super cool Kube Scheduler WASM extension, which is a mouthful, as a framework plugin. So that is the second kind that we talked about before. And this one, it's implementing all the possible extension points, and it will forward the required ones to your own plugin written in WebAssembly. It's running via WAS0, which is the zero dependency, no CGO, grass-fed, organic WASM runtime. That's a favorite in the Go universe. So the code that it's calling is onto the guest side. So this is within the WebAssembly VM, and that code is going to look like this. So this is a very, very simple plugin, which is going to filter the nodes on which a pod can run. That's really important. Please all, you pay attention to this, because we'll come back to this example over and over again. It's receiving 3 parameters. Just forget about the first one, not relevant this time. But you can see the second one is a pod, which is like your entire pod definition, so it can be pretty big. And the one after is node info, which you can think of as just your node information plus a few other things. It's making a decision based on that, and it's returning a status. The status has a code and a reason. The code is going to let the scheduler know what your decision was. And the reason is just a string that is useful for operators. That's what's going to end up in your lovely Kubernetes events. Oh, and one more thing. You can only write a plugin code in Go. And not even in big Go, but just in tiny Go, which is a bit of a sad trombone, right? So, Dejan, what do you think we should do?
So, I mean, I really like the idea of the scheduler plugin framework, and it seems like a perfect candidate for WebAssembly to allow us to write our plugins in any popular programming language. I know Golang, Rust, Java, whatever supports it. So what's the issue here? Why only Go? So do we need to write this? What do we need to do? So
OK, so let's start by looking at the current guest SDK and seeing what it looks like in the WASM scheduler extension. So we understand what we should do to have those other guest SDKs. So actually, we're going to take even one more step back, and we're going to look at the place where the scheduler is handing over to the WASM extension host via the scheduling framework. So this is the filter that we've seen before. As you can see, it's taking a pod and a node info. And then it's doing all kinds of ceremony there that's happening. We're pushing the pod and the node name to a stack. And actually, what you don't even see here is that there's a pre-filter before. The pod is going to be serialized into protobuf and put into a buffer in memory that can be called later. And importantly, it ends up here calling into another filter function that is still part of the host. And that one does a bit more ceremony and ends up doing this thing there, which is basically, let's tell WA0 to jump into WebAssembly land. So jump into WebAssembly land, we land into the guest SDK. So this is code that the user is not writing. This code, if you look at the function signature, it's taking nothing, and it's returning an integer. And the reason why is because basically in core WebAssembly, you only receive pointers and integers, and you return just one thing. The pointers and integers that I'm talking about, they actually put on the stack, so you'll need to retrieve them from the stack. This is actually happening a bit further. You see this import.current node name. This is calling into another piece of code of the guest SDK, and there you see this mem.getString. This is actually doing all kinds of memory shenanigans so that it can call into that Kate scheduler current node name, which is an exported function, an imported function. So that's a call back into the host. And that one is going to be given a pointer and a limit, and it's asking, please, Mr. Host, can you put a string with the current node name into this buffer, which is in my memory, so that I can then return that. And you can see that there's quite a few other places where it's calling back into the host and doing all the memory shenanigans. I'm not going to show you each of them. You can see that status to code. That's the one that's going to be responsible for putting that reason string into a buffer that can then be read by the host. Eventually, we reach this filter thing. And this is finally the code that the user can write. Cool. So this is fine, right? Let's just write a Rust SDK and a Python SDK, do all the glue and all of that, and yeah, no. One does not simply write multiple guest SDKs. That would be just super unmaintainable. We would need to keep them in sync, all of that. Like, surely, Dejan, there must be a better way.
So, yeah, actually there is. So for the past two KubeCons, the component model was very hyped. We attended a lot of talks, and we really were impressed with it. So it sounded really interesting. We heard some really promising things, like the canonical ABI, complex types. So we had an exciting idea. Let's bring the component model to the Kube Scheduler WASM extension. What does that really mean? So with the component model, we get a standardized language-neutral way to define clear interfaces and structures, like the ones you can see on the slides. We can describe our structures, the complex Kubernetes structures, like for a pod, for a node. We can also define and export our plugin methods. Here, we opted just for a filter for simplicity, but this allows us, so what Jonathan was showing and all of the complicated function calls, whatnot, and then doing this in any other language, this will ultimately allow us to auto-generate all of that stuff. So, first thing which I was really excited about was when different languages need to communicate, so, and especially when sharing complex structures, one major challenge arises. So how do we safely pass data across language boundaries without losing information, without risking errors, or adding complexity? That's precisely where the canonical ABI steps in. It's a standardized, low-level binary interface designed explicitly for the component model. It specifies exactly how complex data types should be represented, how they should be serialized, and how reference should be managed. So here we can see on the host side, this is in Rust, and Rust has an amazing macro called bindgen, where you can point it to a WIT, and it automatically adds structures and functions into scope, like you see here. So what we can define in a WIT, here we can reference it. We can instantiate a pod, instantiate a node. We can call the filter. We can pass the complex structure. So that's a lot nicer than what we had before. And also what we can do for the guest SDK or for the plugin developers, we can automatically generate bindings, generate automatically all of the glue, and then a developer will just focus on writing the actual logic. So why generated bindings are important? So if you ever tried manually creating language bindings, I guess you know the pain. It's tedious, it's error-prone, and most importantly, it's not maintainable. Because if we did write a Go SDK, Rust SDK, Python SDK, who will maintain that? It will just battle with incompatible versions. Some will be better maintained, some not. The component model makes this problem practically disappear. So thanks to the standardized interfaces, the canonical ABI, we can generate all of that. So what Jonathan showed you, pretty much we can just generate it. So pretty much, yeah, like the meme shows. You get a binding, everybody gets a binding.
that is just like, that just sounds awesome. So let's go, refactor the project, and just like use the component model.
Yes, that was the plan. But, well, the reality hit us hard. So we were hyped. We thought component model will save us from all of the troubles. We just go, refactor, and everything is perfect. But first thing which we started was, OK, we need to define our WIT. And we were like, OK, what now? Do I need to rewrite in the WIT? Do I need to rewrite the Kubernetes structures? So here's an actual pod spec.
That's a small one, even.
Do I need to rewrite this in the WIT? Do I need to do the same for the node? So we were like, well, nobody would do this. That's not maintainable. I guess, let's see, is there any WIT generator? Something like, can we generate WIT from Proto? Sadly, we cannot. We're like, OK, is there something for OpenAPI? We found some project, but we didn't have any luck with it. So OpenAPI to WIT was a no-go. We were hoping, like, let's go structs. But sadly, Go structs to WIT was also no-go. And yeah, that was our first road bump. Well, we need to reuse external types. I mean, for any integration, we cannot just write by hand manually into it. So nonetheless, we were like, we want to try to make it work. What's the next thing? So now we needed to run our filter component in a Go host. Why a Go host? Well, the Kubernetes Scheduler plugin framework is written in Go. The Scheduler WASM extension we've been working on also in Go. It uses WAS0 as a runtime, so picking WAS0 was our logical choice. Soon we realized, well, we cannot run components in WAS0. We searched for the GitHub issues. There was one about plans to support the component. The general sentiment was currently they aren't planning until some prerequisites are met. We're like, OK, what are other options? Wasn't time Go. We tried it. You can see Wasn't Time Go still isn't ready. It's missing a couple of things. They're being worked on, but that left us in a bit of a pickle. So we don't have a Go runtime. We could hack it. We could use Rust and the scheduler extender to make it work, but that's not really what we wanted to do. So Jonathan, on your part, was it a smooth sail or?
So the first thing I did is try to look at alternatives. And actually, there is a really good alternative. There's the top contender of the alternative. That's Xtism, which has an interesting logo. Xtism supports many hosts and guest languages. One of the host languages is Go, using WAS0, so happy days. That's good. And in terms of guest SDKs, as they call them, the PDKs for plugin development kits, you can see it supports Rust and JavaScript and Python and C# and Go and many more, actually. So how do you use it? So you do a little bit of ceremony again to just load your WASM module, and then you end up using this plugin.call function. Just give it your function name and a single input. In this case, it's bytes. And it's giving you back an exit code, a single output, which is again bytes, and a Go error. So let's look at the guest side. In this case, I chose Rust, but as I said, like it works with many programming languages. This is using the PDK. It's got that nice plugin FN macro, and so you end up just getting inputs, bytes in, bytes out. Pretty cool. We can probably do something better. So you can use it with strings as well. In the case of the Go host, you need to convert. But on the guest side, it's pretty neat. See, function signature, just getting string as an input, string as an output. Again, happy days. Where it gets even more interesting is that you can also use JSON to pass things around. So let's just say that we define a JSON schema like this one. So we take the existing Kubernetes JSON schema, and then we add our filter inputs. The reason why there's a filter input object here is because you can only have one input. That's one of the requirements of Xtism. And you see my filter input as a pod and a node info. That's, again, the same thing for the filter that we've seen. On the Go side, it looks like this. So you've got a filter input at the top, the struct. You can have that auto-generated. There's many projects like QuickType that can take a JSON schema and just generate it for you. You can even generate a JSON schema from Go struct. So all of that is fine. You just initialize it. You have this JSON marshalling of the input and the output that are around the function call. That's a bit unwieldy. That's a bit of ceremony, but it's fine. That's the host path. Like, that's not what the users need to look like, and we only need to write that once. On the guest side, it's actually super neat, because Xtism provides the plumbing so that we can receive a nice native complex type and return another one. What I didn't say right before, so when I showed the bytes example, is that it's doing all the memory shenanigans that we saw before. Like, it's not magic. It has all that glue code. It's just that they wrote it for all the guest SDKs for us. OK, so what can we do if we care about performance? Well, we could use proto. So this is a proto where I'm referencing the other official Kubernetes proto packages, and I'm defining my filter input again, which is a pod and a node info, blah, blah, blah. So what does it look like on the host side? It's very similar to what we've just seen with JSON, because on the Go host side, you need to do all of those things yourself. I'm using WITty proto, which is much faster than regular proto, to marshal and unmarshal around. And then on the guest side, well, that's a bit of a letdown. We don't have all the fantastic stuff being done for us yet. So I'm just taking bytes. If you see that filter function at the top, I'm doing a bit of ceremony so that I end up unmarshalling and marshalling and calling the real filter implementation, which again looks pretty neat. So that's not too terrible, but it's a compromise between you want performance, you want ease of generation of guest SDKs. Briefly, some runner-ups in terms of alternatives we tried. There's XTP bindgen, which is from the same people that made XTISM. It's built on top of XTISM. It's quite interesting because it defines a schema that looks a lot like OpenAPI. So the cool thing is that you see again in component schemas, I've got my filter input once again. So this is just, this is YAML, but basically it's again a JSON schema definition. And what you see above is exports. So there you can actually define the signature of your functions. And then it's going to take this and it's going to generate even more of the glue code for you. So it's going to already generate the function signatures and all of that. That sounds pretty cool. I've tried to just convert the Kubernetes OpenAPI schema to this, and then I ran the XTP command line thing, which is proprietary, and calls into some open source bits, and it just didn't work. It crashed. So, yeah, that's sad. It probably can be fixed. Another quick mention, this Go plugin thing, that's not the HashiCorp Go plugin, it's another one, I cannot pronounce this. It's doing all the stuff with WITty Proto and all of the memory pointer passing and all of that. It has a Go SDK for the host and only a guest SDK in Go. So we're, again, back at square one. But there's a new hope. There's a new project that was released in January called Gravity. And Gravity is very, very early at the moment, but it's essentially a transpiler. So it is trying to build on top of WA0 to implement the component model. At the moment, it is still super, super early. These are the only types that they support. That basically does not allow us to have all the complex types that we wanted to have. Also, we still have the lack of proto generation, but it's really going in the right direction. And I've basically tried a couple of benchmarks. I'm gonna go very briefly about this. So there's a lot of stuff. Start from the left. This is a Go host using XTISM with the JSON method and then running various guest SDKs. You see they're all about in the same ballpark. Then skip the second one for now, go to the third one. This is when using WITty Proto, so obviously this is faster than with JSON. And just as points of comparison, I've tried to use Gravity with a Go host and with using JSON. So I'm just using their string types. So there isn't the advantage of having the entire richness of the component model. But if you look at the green bar over there on the first green bar and that fourth green bar, you can see that it's just for sending a string, even just for that, it's already a little bit faster. I'm not sure why, but it's going again in the right direction. Then we've also implemented a host in Rust that is using WIT with just a super small subset. So it's not exactly an apples to apples comparison. But if you look there at the gray bar, this is a tiny Go guest that is running or plugin, or I should have said that, but it's basically doing a little bit of regex filtering. It's a filter plugin that is reading an annotation from the pod, from the pod, and if it finds a regex, it will compile it, it will apply it to the node name, and based on that, it will filter yes or no. So a tiny bit of logic. The tiny Go one, the gray one, that is running with the component model, that is running with WASM time, and you can compare it to the second gray bar, which was the same piece of code, but using JSON in WASM time. And you can see that this gets us a lot faster. And then finally, just for comparison, because some people are like, why are you doing all of this stuff? Like, why are you using WASM? Just call into a shared library or do something like that. It's not free. You will end up with the exact same problems of having pointers and all of those things. So you will end up also either having to share your memory, which is super dangerous. Like, we're writing stuff in Go, we want safe memory. We don't want to just hand it over to some C library and then just crash. And I forgot my train of thought. The point is, this is JSON serialization in a Go host, calling via CGO, a library, a shared library written in Go as well. And you can see the performance there is in the same ballpark as what we would get with WIT. And now, Dejan, what are we asking our audience?
So, as we heard in a previous talk, issue with WASM P1 is everybody does its own thing. Component model is an amazing idea. Component model standardizes a lot. Component model can make things so much better, but it's still in its early stages. So we want to do a call out to all contributors. So the tooling lacks a couple of things. So the WIT generators, proto to WIT, JSON to WIT, Go structs or whatever to WIT. That's something. For Go, let's decide what we want to do with Go runtimes. Will WAS0 support it? Will WASM time Go support it? So I think this should be a joint effort. So whoever is interested, we urge everybody to get involved, to contribute, to discuss, to join working groups. And also, we'd like to do a shout out to all of the maintainers, to the WASM Runtime Technical Advisory Group, to everybody who is involved in these projects, the WASM community, the authors of the component model. So you all did an amazing job. And it leaves us.
And one more thing, which is that the component model really is the way. We are quite convinced about it. And if we just like all pull together and we make it happen in Go, this use case that we've shown is just one use case amongst many other use cases in the whole CNCF landscape. We've got Go everywhere. What if we could just extend it and not have to do that glue over and over and over again in each project? We just do that once, and then we will all benefit from it. Do you have any questions? So I believe if anyone has a question, that they should walk to the mic that's there in the middle.